Again. So refraction. First of all, let's define the refraction. Before defining that, let me just give you an example. For example, there is a coin inside of a glass without water, and when you put the water inside of the glass, you are going to see the coin in a different shape. So the reason here is due to light, due to refraction of the light, this is going to happen, okay? So the refraction means the speed and direction of the light change when the light gets into another medium. For example, here, the light is just inside of the glass, right? But here, what happened in the second one, in the second part, you put the water inside of the glass and the glass changed its like medium. The medium was air over here, and when you put the water over here, the medium change into water. Okay, so we call this refraction of light. Okay, when you put pen, for example, inside of water, you are going to see the same phenomena over there. So the pen is going to be seen like broken. So here, for example, when you send there is air, medium air over here, and there is water over here. When you send light from air to water, what's going to happen? The light is going to be broken. It's going to bend towards the normal. We are going to put a normal over here, which is 90 degrees. So since the density of water is greater than the air, the light here is going to bend towards the normal. Okay, it can be reflected as well if the density difference is very much bigger. Okay. So we consider the speed of the difference in vacuum and air. The speed of the light. Remember that is different. So we represent the refraction of the medium by n, the small n over here. Okay. So we have a question. What is the normal? The normal. We put a normal over here in order to define, in order to put the refracted or incident ray. Okay. We put a normal over here, which is 90 degrees to normal over here. Okay, it is 90 degrees. It gives us a clear idea where the refraction will happen. It is going to happen towards the normal here, because the density of the water is greater than the density of air. Or when you change the places, for example, if you send from water to air, then it's going to go away from the normal. Okay, that's why we need a normal. We need a line over here in order to define the refraction of the light properly. Okay. So let's continue. So the speed of the light, remember, in the air is 3 times 10 power 8 meter per second, right? It is around 300 million meter per second. Okay. We use the formula to find the refraction. We use formula speed of light over the speed of light inside of the other medium. We use that formula. So to get this straight, we are going to use Snell law. There is Snell's law. What does Snell law state? Snell law state when a medium enters when a light ray enters another medium, it can bend towards the normal or it can go away towards the normal. This depends on the medium's density. Okay, so this is going to be our incident ray, and this is going to be our reflected ray. Okay, incident and reflected ray. So we can apply the Snell laws here. Let me just go forward. So we are going to apply the Snell laws over here by using the formula. Since the speed are going to be the same, we're going to use this formula. n1 times sine theta 1 equal to n2 times n2 is going to be the second medium times sine 2 theta. Okay. When we use this formula, we can find the refraction of the light inside of another medium. There are some materials and their mediums, their refraction over here is given. For example, diamond has at 20 Celsius, which they are solid, it has like 2.41, 2.419 refraction. For the glass, this changed to 1.5. For liquid at 20 Celsius, carbon tetrachloride, it has 1.4. Ethyl alcohol, it has 1.36, and water has 1.33. For gases at 0 Celsius, 1 atmosphere, it is going to be like for air, it's 1. For carbon dioxide, for oxygen, for hydrogen, they're all almost 1. They are very close to each other when you talk about the refraction, because they are gases and they have similar refraction. Okay. So let's go to over some rules over here. So rules of refraction: from less refraction or less dense to high dense. What's gonna happen now? So as I told you, when you send the light ray with 90 degrees, it's going to go straight with 90 degrees. The second level, when you send with an angle, you have to put a normal over here. Since the N2 is greater than N1, normally, if these two medium were the same, what would happen? The light ray would continue like this. But since is N2 is greater than N1, it's going to bend towards the normal, okay? Since the N2, the medium 2, the density of medium 2 is greater than density of medium 1, the refracted ray is going to get closer to the normal. Okay, it's going to bend more. The second one, the second solution, the second part, this time the second medium has less denser than the first medium. So what's going to happen now? Again, when you send 90 degrees, it's going to go straight. But if you send with an angle, again, you have to put a normal over here. Then what's going to happen? This time it's going to go away from the normal, okay? It is going to be broken away from the normal, as you see over here. So the theta 1 is going to be greater than theta 2. Why? Because the N2 is less than N1. The N1 is less denser than N2. That is the reason, okay? All right, let's continue. So you can just change shapes and send different rays over here. They're going to change, okay? So we have critical angle. It is called as when you send an incident ray with a critical angle, it's going to go with 19 degrees. It's going to be reflected by 19 degrees. Okay, we call that angle critical angle. Critical angle. So to find a critical angle, we are going to divide the N1 over N2. Okay, the normal the refraction of N1 over the refraction of N2 is going to give us the critical angle of the incident ray. Okay, to find the critical angle, we are going to use that formula. So when the critical angle is smaller than the incident angle, then it's going to be total internal reflection. So total internal reflection will happen when theta 2 is greater than the critical angle. Let's say critical angle is 60 degrees and incident ray you send, it is 65 degrees. So it is not going to be, it's not going to go past through the second medium. It is going to just reflect inside of the first medium. So we call this total internal reflection. Okay, so total internal refraction, how can we apply this? We can apply this like, can we confine light within the medium? Yes, we can. In total internal reflection, light is confined within the medium. Okay, in total internal reflection, light will be inside of the, as you see over here, inside of the medium. So image formed by refraction, how does image form by refraction? Let's go over that too. Again, this is N2, water, N1, let's say air, and N2 is greater than N1, the refraction of N2 is greater than N1. So what's going to happen? When you look at N2, when you look at it with 90 degrees, it's going to go straight again. But when you look at it with different angles, again, it's going to get closer to the, it is going to be bent towards the normal. When you put a normal over here and over here, you are going to see that light is going to refract it towards the inside of the second medium. Okay, so we can apply here again over here the formula. This is a concave lens over here, as you see, it is concave. So let's continue. We can apply the Snell laws over here. So N1 sine theta 1 is going to be N2 times sine theta 2. So if the angle is small angle, approximation sine theta we're gonna take it at theta, right? Angle is in radians. We are gonna take that, and we can use just formula over here to find the we can find the approximate relationship between triangles as follows, like these triangles. We can use this formula to find total refraction inside of a medium. Okay, so there is an example here. Gaze into the crystal ball, and a dandelion seed ball 4 centimeter in diameter is embedded into the center of the spherical plastic paperweight having a diameter of 6 centimeter. Diameter is 6 centimeter. The index of refraction of the plastic N1 is 1.5. Find the position of the image near to the edge. Seed ball. So again, they're gonna draw our shape over here. Since the diameter is 4, we are gonna take the radius, which is 2, and the diameter of the paperweight is 6, we are going to take its radius as 3. Okay, so we can apply the formula over here. Again, n1 is greater than f2, so n1 over do, which is distance of the object to the second medium, and the distance of the first object. When you do that, they're going to get the radius 1.5 over 1. This is n1, and 1 over di. We don't know di. We are looking for di. So again, it enters from airs to water. So it's 1 minus 1.5 over -3. Why -3? Because the radius over here is taken as -3. That's how you get the -3 radius. So, and here when we apply this, we are going to find the image of the near edge of the seed ball as -0.75 centimeter. Okay. So let's continue. So flat refracted surfaces, flat, again for the flat surfaces, again, if you change the medium, there is going to be reflection. If the mediums, their density are not the same. If a refracted surface is flat, then R is infinite. That means the radius is going to be infinite. Okay. And then we are going to find the formula over here. I'm not going to stay over here. Let's move on. Actually, you don't need to know this. So we need to know about apparent and real weight. Apparent depth means when there is an image over here. For example, there is a bear over here. It's looking for fish over here. Okay, how bear is going to see the fish? Since the air is less denser than the water, it is going to see the, like, one bear look at the image of the fish over here, it's going to see differently. Okay, it is going to be broken. So to find the di over here, we're going to use this formula: negative n1 over n2 over times the do. This is going to be our the real weight over here. Okay, this is apparent weight. This is going to be the real weight. Apparent depth, real depth over here. Okay. So the same thing is applicable when you go to the fishing. You are going to calculate. You see actually apparent depth. You see apparent depth, but the real one is going to be real depth. You cannot like consider that. If you see like the object is 30 centimeter close to you, it is not true because you are looking from a different medium. So probably the object is like located 60, maybe 50 centimeter away from you. So you have to use this formula to find the real or the apparent depth. Di is the apparent depth, do is the real depth over here. Okay. So we're from less high density to less density again. When you look at it again, you're going to see the object far away, but the object could be closer than you think because of the density difference. You're going to see the object like that. Okay. Again, to find the di, again, this time we are going to use, since you are looking for from the higher n to the last one, we are going to use n2, which is this part, over n1 times do, the real weight. Okay, this is going to give us the refraction of the object. All right.